Continuing with this theme, let's see if we can recognize when limits exist, right? Recognize limit values, and when they don't exist. Not exist. And this will be from a graphical approach. So we'll make another picture with a function which is somewhat more subtle than we had a second ago. Maybe something like this, perhaps. That will do. It's hard to tell, but that is a hole there. Just trying to make that appear as a hole. Right? This is a filled in point on the function, and there's a hole there. There's f of x, there's x. Scale is 1. So that's height of 2, that's height of 1, that's height of 0, height of -1, height of -2, and so forth. And we'll scale by 1s on the x-axis as well. 1, 2, 3. This will be good enough. All right. So let's look at the limit. We want to look at the overall limit. The question might be something like f of x as x approaches 0. Question mark. What is that? So we'll look at it in two stages. I want to note first the limit as x approaches 0 from the left. What is the function approaching? Well, as x approaches 0 from the left of 0, with numbers which are slightly less than 0, which of course will be negative in that case, heading towards 0, the function is heading towards a height of 0. Now, the function is not actually 0 there, right? This is not filled in. The height is actually 2, but what is the function heading towards is what our limit cares about, so the answer is 0. Limit of the same function as x approaches 0 from the right. Again, that's all those superscripts mean. Direction of approach. What's it going to be? So as x approaches 0 from the right of 0, we have that the function is moving down these values and heading towards a value of 2. And the function does happen to define there and is a value of 2. But that's irrelevant. Even if this had been a hole, the answer to this second limit from the right would have been 2. Overall, we see that these do not match. So therefore, since this is an if and only if statement, since the two left and right hand limits do not match, they are not equal, right? Even though they both have a finite value, but that finite value is not the same, right? This is 0, this is 2. So therefore, the limit does not exist overall, and therefore the answer to question mark here is D and E, i.e. does not exist. That's our abbreviation for does not exist. Next, take another example. Something like this. And then here is perhaps. Okay, again, scale is 1. Scale is 1. And so forth. Again, we ask the question. I'm just picking 0 to be what x is approaching. Could have been anything. I'm just making the graphs very simple. We know the limit of f of x as x approaches 0. We want to know the two-sided limit. And we will again look at what happens from each side. Limit of x approaches 0 from the left. What is the function approaching? As x approaches 0 from the left, as x approaches 0 along the x-axis, the function is heading down towards a value of -1, even though it does not achieve that value. So therefore, that is -1. That is a defined limit. Right? limit as x approaches 0 from the right. As x approaches 0 from the right, here we go, heading towards 0 along the x-axis. What happens? The function is heading up towards nothing in particular. All right, it looks like we have a vertical asymptote here. So the function just keeps getting larger and larger and larger. You might say it's approaching infinity. And we will say that. I'll write that right here. It's approaching infinity on that side of the asymptote. But nevertheless, that is d and e, because that is not a finite value. That's not a number. Infinity is not a number. It's simply some qualitative statement about what the function is approaching, i.e. it's just getting larger and larger. But it doesn't make it exist since it's not a number. Matter of fact, this type of limit has a particular name. It's called an infinite limit. But even though it's called an infinite limit, right, it has the name limit in it. It doesn't matter. It's not really a limit at all. It's not defined. They just call it infinite limit. So overall, right, the two one-sided limits show us that the overall two-sided limit must be d and e as well, because they don't agree. Not only do they not agree, one of them is non-existent at all, so therefore how could the overall limit be existent? Example 3. I will use a concrete example now. We'll use an actual function with a title. Okay. We will talk about f of x being sine 1 on x. F of x equals the sine of 1 on x. All right. So let's again find the limit of this function as x approaches 0. What is it going to be, if anything? Will it exist? Will it not exist? All right, so we will look at, firstly, the limit as x approaches 0 from the right. I'll go ahead and fill in the function rule here, since we have it. Okay, question mark. We have a complicated example here. So if x is heading towards 0 from the right, we're dealing with numbers which are very close to 0 but slightly above 0. Therefore, this ratio is always positive. But 1 over something very close to 0, that, of course, all right, 1 over x then is heading towards infinity. It should be pretty obvious, right? As a fractional denominator gets smaller and smaller and smaller in magnitude, the overall fraction value, the overall ratio value gets larger and larger as long as the numerator would stay fixed. All right, so if we think about the sine function, we've got the argument of the sine function heading towards infinity. So what is the overall sine function doing then in that case? So if we just draw out the sine function, we can remember what that looks like. Let's see here. Sine function. All it does is what? Oscillate between -1 and 1. So -1, -1, 1, -1, and so forth, right? Forever. So to the other direction, same structure. -1, 1, -1, 1, forever. All right, that does not look as nice as I had hoped, but nevertheless, it'll illustrate what we're trying to talk about here. 1 and -1. All right, we know the range of sine. Instead of using x here, I'll use a different variable. We already have x over here. I'll use alpha or something maybe. So we know sine of anything is trapped between -1 and 1. That's the range of the sine function. Whoa, where wrote -1? There we go. And so over here is our, I say alpha axis. Here's sine alpha. And so we see what happens if the argument of the sine function gets larger and larger. This is happening here, right? The argument is getting larger and larger altogether. Not just the x, I'm saying the 1 on x, getting larger and larger. So that means we're moving out here, right? X, or in this case alpha, sorry, alpha is heading towards infinity, right? I.e. the 1 on x value is heading towards infinity. What is the sine function doing? It's just oscillating back and forth, right? oscillating between -1 and 1 forever, right? It's not approaching anything in particular. Any particular value. So therefore, even without analyzing what happens as x approaches 0 from the left, although it will be quite similar, we already have the approach from the right as being dne. So therefore, the overall limit is also dne. Could not be otherwise. And these three scenarios are the main ones you'll see where the limit does not exist. First one being what you would call a jump discontinuity. Second one is another type of discontinuity. Clearly, it's also not connected, right, at the asymptote. So that's called an infinite discontinuity. And then finally, although this is not discontinuous, nevertheless, the limit does still not exist because you have what you would call an oscillatory function. Right? Oscillating between values and approaching none.